That's one thing to my credit, not to his, of course. Brent is one of the major players in observational cosmology in the nearby universe out to 300 million light years or so. He has, for example, came up with what is called the Telly-Fisher relation. Now I have to give you some information about that. In this talk, he will not call it the Telly-Fisher relation. He will call it the line with what? Luminosity relation. And it is very confusing when you hear him give this talk about that. There is a line with luminosity relation. Why the hell don't you say Telly-Fisher relation like every other astronomer in this universe? No. So he came up with this relation. This relation is one of perhaps the most important relation with which we probe how galaxies move in the universe. It gives us a tool to measure galaxy distances. Not only that, it actually is one of the most important ingredients for galaxy formation modelers, because galaxies, this is a relation which involves spiral galaxies, the total velocity of a spiral galaxy versus the circular velocity. And I'll just mention one aspect of it. For example, the late Jacob Bekenstein and Monty Milgrom, they give the Telly-Fisher relation as one of the best examples for modified gravity theory. Because in that theory, it actually comes out in a very straightforward matter. And for the standard model lambda CDM, it's very difficult to get actually. We have to be honest about that. Brent is, I already said, he's a leader, but he's not one of these people who go to a meeting and they start shouting, I'm right, you're wrong. And I want to give you an example of that. I was in Leiden with him, and there were about 15 other participants in this meeting. I had my GPS. I wanted to go to some restaurant downtown on bicycles, and I had my GPS, but people, of course, followed Brent. Brent got to a dead end. There was no road, nothing. And I told them, now we have to follow the GPS. And I started cycling alone, thinking that they would follow me. No, they didn't follow me. They followed Brent somewhere. And they actually got there before me. So he's this type of person. There is also, I got to tell them so many things about him. One more thing. There is something called the Tully index. The Tully index is a very interesting index. It's the number of countries you visited divided by your age. For Brent is 1, and I'm not going to tell you his age. But I'm going to tell you the number of countries he visited. For me, this index is about half, or 0.6. So this is the Tully index. You can try to compute your own Tully index. I'm pretty sure, no matter what age you are in this audience, this is going to be less than 1. It's very good. Please, Brent. I'm happy to have you. Go ahead.
Okay, Adi, I'm glad you didn't tell about that trip to the disco in Berlin in 1995. Okay.
I was trying to forget that. I thought you also wanted to forget it.
Yeah. Well, I'm very glad to be here. This is a really nice event. And I'm going to tell you a little bit about this Laniakea thing that's got a little bit of press here. Let's see. So this is some of the players. There's a lot of aspects to this program, actually. This particular part of the program, though, these are my collaborators. Yehud is here, and Hélène Courtois, Daniel Plummer, and his friends are not with us here. But let's see what this story is all about. So it's now become apparent in the last 30 or 40 years that there's a lot of structure in the universe. There's clusters and filaments and moids. And there's a couple of different ways that you go about analyzing this structure. The traditional way has been just to look at where these galaxies lie on the sky. You get their spectra that will give you the third-dimensional distance. You know where they are in the sky, and then you know roughly how far away they are just from the Hubble expansion law. So you could observe that distribution, and you could predict the velocity field from that with some assumptions about the relationship between mass and light. There are deficiencies because there's always an incomplete sky coverage. For example, there's this open obscuration, an obvious problem in that area where we just don't have much information. And then there's this issue about how, in fact, are mass and light correlated. And this is actually one of the really interesting things we'd like to learn about. And the other real problem with the redshift survey is there are very large long-range influences, and we don't get those influences from the information from the redshift survey. Now, alternatively, you can get information from velocities, just on the supposition that velocities have grown through the perturbations of the gravitational field. And so if you just observe the peculiar velocity, and this funny word, peculiar, for those who aren't in this game, there's the Hubble expansion most galaxies are rushing apart with the Hubble expansion, but there are extra velocities that they have because of the gravitational influences, and astronomers use this peculiar name, peculiar velocities, for this added on velocities that arise from gravitational fields. And so we can anticipate what the field is from that. The trouble is that the errors are very large in individual measurements, and okay, you could have systematic. But overall, we see that our basic idea is correct, must be correct, that these peculiar velocities arise from density fluctuations. So this is the survey we're going to do. Oh, I have to advertise a meeting that's coming up in Vietnam. So here's the basic thing that we're doing here then, with this. So our group here is meeting this clues collaboration, which involves a whole bunch of different aspects. The part that I'm involved with are in this top box. I've measured distances of galaxies. These peculiar velocities I was just mentioning are derived from observed velocities, which are very good. That's something we know very well. And then if you can take off the Hubble component of that due to the expansion of the universe, then you can get peculiar velocities. Well, if you can get peculiar velocities, then you can infer in techniques that I'll talk about three-dimensional velocities in the density field. And other aspects of this clues program involve running the show backward to initial conditions and then simulating how the universe might evolve, and various people down here are involved in that program. Now, there is a problem here, though, that the errors are very large in distances, and especially at larger distances, and that means that there's big errors in individual peculiar velocities. And the situation then is that we have actually very good distances locally, but they degrade badly with distance. Now, there's been 3 editions of this distance catalog that I'll be talking about. The first one was something we call Cosmic Flows 1. Here's people that were involved in that. It came out in 2008. We had 1,800 galaxies in that particular edition. And the main takeaway from that early work was that our galaxy has a large local velocity. So this map over here, each dot on this map is an individual galaxy. We're at the center here. And all of our neighbors around here have all these nearby galaxies to us have green colors. That means they have very small peculiar velocities. All these galaxies down here have are colored blue because they're moving towards us. And all of these are reds and browns because they're moving away from us. Well, actually, what we're seeing here is that a reflex of our motion, as the arrow might indicate. I'm actually going to do, just take a second here, because I've run into a little technological difficulty. Namely, one of my hearing aids has dropped its battery. So if I might just change that battery, and then we'll continue. Not an elegant thing to do here. But it's a good thing to be able to hear. Sorry about that. Usually I'm better. Okay. So, on with my story. Here's just a summary of what I was just talking about. This is a nice plot of, we're looking at a projection onto the local universe where we're located here. And over here is the Fertile cluster. And there's a filament of galaxies underneath us here. And you see everything here is colored blue, as in moving towards us. What in fact is happening is that we're moving in this direction down here, along with all of our neighbors. And why are we doing that? Partially it's because we're being pulled towards this Virgo cluster, which has almost 10 to the 15 times the mass of the sun. And up here we're being repulsed by this void that's up here that's expanding. And so we have these two components of our local motion. Well, okay, then in 2013, we came out with Cosmic Flows 2, and it was a compendium then of 8,000 distances. And, okay, I must be less modest now because I'm now calling this luminosity line with TF, if you see TF. There's all these other techniques, though, that we have for getting distances to galaxies. Amongst them are things like the pulsation period of Cepheid variables, the intrinsic luminosity of stars at the tip of the red giant branch in old populations, supernova, which are very bright events that can be seen at great distance. So, and all of these people down here have been involved in that paper. So we have 8,000 distances. We're all homogenized, and where the ones in red here are our own contributions, things we've done ourselves, and all the black things here are we've embraced information from the literature. Now, most recently, and in fact not quite fully published, is Cosmic Flows 3. And now we're up to 18,000 distances. So you saw we went from 1,800 to 8,000, and now 18,000 distances. Most of what I'll be talking about, though, today will be still based on reconstructions done with the second edition of Cosmic Flows 2. I'll only be mentioning a few things that have come out already with respect to this new edition. This is just showing on the sky Cosmic Flows 1, Cosmic Flows 2, and now Cosmic Flows 3 is available now. And here's, so most of what I'll be talking about is based on this individual case here of Cosmic Flows 2. This is the velocity histogram of all of the galaxies where we have measured distances. And what I'm showing here, velocity on this scale, that's something I'm calling the Hubble parameter here. The Hubble constant is velocity is divided by distance on the mean. And for each individual galaxy in my sample, I can measure velocities at distances and get a Hubble parameter for each individual object. Okay, so this was Cosmic Flows 2, and it was consistent. It was a Hubble constant around 74. Now, Cosmic Flows 3 has all of these new additions. Here's the velocity histogram, the number of objects. The total for the whole sample is given by this black histogram up here. There are some major new components in the southern hemisphere, contribution from the 60th Galaxy survey, fundamental plane work in the southern hemisphere. Our own contributions, new contributions, are information using photometry from a space telescope that's called Spitzer. Again, I want to emphasize that today we have really good information locally. So locally we have the situation, here's the vernal cluster over here, here's us here. Again, the colors are indicating peculiar velocity. And again, you see what I showed before, we're seeing it better and better that, first of all, that nearby galaxies have very small peculiar velocities once you've taken out the Hubble expansion. All of these galaxies below the plane have negative velocities. All these galaxies, as you approach the vernal cluster, have positive velocities because they're falling into the vernal cluster. So we're seeing this flow into the vernal cluster now quite well. And up here above the plane, there's not much at all, but we've just, still unpublished, made a new observation, tip of the red giant branch observation of a galaxy that's in the galactic plane that fortunately didn't have much obscuration, and it's coming towards us with this large negative velocity. So we're seeing negative velocities above the plane and below the plane as things compress onto the plane, and also then as we're moving down. So in other words, we're moving down, but this is chasing us and catching up to us from the void. Here's a little movie, something that we've constructed then of the flow in this region here. This is the vernal cluster here. This is Andromeda and the Milky Way down here. So this is a little reenaction of our flow. Actually, you see this little flow that Jenny Source was talking about this morning in one of our talks of vernal moving over here to the left. So this is still not a model we're perfected, but it's a model we're working on. So this nearby, so I'm going to be talking about two ways of analyzing the data. This nearby work, we're in the nonlinear regime for dynamical regime for a lot of what we want to do. And so in this regime, we use this numerical action methodology that Jim Peebles first taught us about, and Ed Shea is the expert. Oh, and Stephen Phelps was actually working here in Technion, or he was working in Haifa for quite a few years. Maybe he talked about this. So anyways, the numerical action idea is that for collisionless systems and the action, which is the integral function over time, and here it is for collisionless systems, the difference between kinetic and potential energy. And we're looking then for saddle points of the action. Now, so we can then form orbits that are plausible orbits if we can constrain 6 elements of phase space. So here we have things that we might want to know. Alpha and delta are positions on the sky. We know that very well. I'm in a game here of measuring distances, so in principle we know this. We can use constraints on either end of the orbits, and so we can use a constraint on the initial condition of an orbit that the velocity dispersions were 0 with respect to the Hubble flow, and that velocity perturbations have arisen over time through the perturbations from the masses. Well, we also then know the luminosities of objects. We might infer something about the masses from mass to light ratios. And we know the radial velocities. Nowadays, for just a couple of objects, we can actually measure proper motions. And so we need at least 6 of these to make an orbit, but we don't know if that's the right orbit. And so we can test on the plausibility of orbits with this kind of a chi-square down here. Okay, So we did this particularly in the case of the local group, where there's a curious phenomenon that's been becoming apparent, that the satellite galaxies around Andromeda Galaxy in particular lie in very thin planes. So this has been quite puzzling. And we decided, looking at the data, that there are in fact two planes. So in the literature, it became, the plane that became very well publicized is in blue here. And it's to be noted too that here's the Milky Way over here, here's Andromeda Galaxy, and here's all these galaxies in a plane down here. And we noticed that everything on one side of that plane seemed to lie in a second plane. So we're actually trying to explain two planes. And then there were a few extra galaxies up here that did not lie in any particular plane. And so we can form, we could determine orbits, numerical action orbits, and we started by looking at the dominant masses. Most of these little galaxies are just test particles in this environment, and the main actors then are our own galaxy and M31, and oh, by the way, M33 is a minor player, but not totally insignificant. All the other ones are just test particles, if you like, and we can try and get one. Now, we don't have enough information yet to uniquely determine orbits. So we made this additional assumption. All these galaxies, companion galaxies, are in a thin plane. We made the assumption then that they are traveling in that plane, that they don't have significant motions normal to that plane. Otherwise, why would the plane be there? It would just be an accidental situation. But that allowed us then to get definitive, no, not perfectly definitive, but reasonably good, reasonable orbits for each of these small galaxies that are around the Andromeda. And okay, I don't want to get too far into this, but it turns out that there's an appearance of rotation around Andromeda. That is to say, all the blue shifted galaxies with respect to Andromeda are on one side, and all the red shifted galaxies are on the other side after you've taken out Hubble motion. And it turns out that all those blue shifted galaxies in our reconstruction always have been lying in a rather thin plane, whereas the red-shifted ones haven't. And so we're not really suggesting that there's a rotation. Anyways, we developed a model. And here's a picture of orbits. This is the verbal cluster. So all the galaxies nearby have been coming out of the local void, chasing after Andromeda and the Milky Way. And these are showing orbits that we reconstructed. So,
but these, of course, this problem doesn't have a unique solution. You have positions today and something far away.
So we have
it's a boundary problem which doesn't have a unique solution.
Yeah. So we have the positions and the velocities today, radial velocities, and
so how typical are the solutions?
Yeah, so they're not unique. We have a second set. It turned out that we had two good solutions for the orbits of Andromeda, Milky Way, M33. Two acceptable orbits, and we're only following one of them. So these are not necessarily the case, but it's just interesting that this was kind of our best case. The interesting takeaway then is given here. So this is showing these orbits from two orientations, and here's the Milky Way, and this is M31 coming down here. So they've been coming down out of the local void. This is the equatorial plane of the local supercluster. These two big galaxies have been coming down out of the local void, being chased by all of these little dwarf galaxies. okay, the blues and the red here are the companions to Andromeda, and the other two colors are companions to our own galaxy. But it would seem that they've all been coming down chasing the two big galaxies, and in particular the two planes that are seen around Andromeda are formed as Andromeda comes towards us, and these other guys are chasing and catching up to Andromeda and following along in a kind of shepherded way. So it's not.
How do you measure the transverse force?
How do we measure what?
The transverse force.
Well, the transfer velocities are only known for a couple. And of course, that will be the real test of our model. So right now, what we're doing is presenting a physically plausible model, a correct model, if you like, with respect to the masses, but it's not necessarily a unique model. So now what we want is to get observations of the transverse velocities and see if we're on the right track. Okay, so I've just finished now sort of part one of my discussion. I'm now going to a larger scale. I'm going to be talking about this Wiener filtering and large scale flow. The difference here being that now I'm going to a regime where the linear approximations are reasonable. If we get in close to if we start to get into complicated orbits, then we have to, then the Wiener filter isn't appropriate. But here it's the same model region of the sky that I was just talking about, Virgo cluster, ourselves here, and with the Wiener filter then, which I'll describe a little bit more after, but we're seeing a flow up towards the Virgo cluster, and then there's a flow across to some place called the Great Attractor. Now, so I'm moving to larger scales. Here's some reconstructions we did actually just with the first version of cosmic flows, but just as an example of what we can get. Here's the Virgo cluster. Here's us at what I view as Snoopy's nose, and here's a big void up here. So this is the region then that I've been discussing a lot, that there's this big void, an evacuation of the void, a flow towards the Virgo cluster, and now I'll start to talk about other aspects of the problem. So, okay, so Yehuda Hoffman, who's here someplace, whoever he is, there he is, has been our guru on this particular methodology, Bayesian procedure, where we assume a lambda CDM universe with a certain power spectrum, and then it's constrained. Then we do realizations, which are then where the model must fit the power spectrum plus the observations. Okay, and then we do multiple realizations to evaluate how well we're doing. As I said, as we get beyond a few megaparsecs, around if we're talking about scales larger than a few megaparsecs, we're in the linear regime, and the good thing that really makes all of this work is the coherence in flows on very large scales. Now, one of our little tricks here is that I'll be talking about that involves decomposition of the flow patterns. So we can measure then from our observations large-scale global flows, but we can break this into two parts by isolating an environment, looking at the gravitational field that we've deduced for this region, and then identifying the local flows in this region, and then vector subtracting that off the full flow to get a tidal flow. Now the other trick that I'll be talking about here that's really quite interesting is looking locally at the shear in the velocity field, and then defining from the basis of the shear tensor eigenvalues properties of local regions, whether it's a knot because there's inflow on all three axes, a void because there's outflow on all three axes, or something in between, which we can call a filament or a sheet. Okay, so we can then start to do these reconstructions. Here's a map with where the little black points are galaxies out of the slice, and here's a reconstruction we did early on. I'm going to just take a diversion here to talk about an issue that's quite topical right now, the Hubble constant. So mostly what I'm interested in here are deviations from expansion. But in the construction of the catalog, we do have an absolute 0 point and a measure of the Hubble constant, the overall expansion of the universe. And this is an issue that's quite topical, as I say. So I just wanted to explain what we're getting. So I described how we actually have 6 different ways of getting distances, and amongst them is supernova. Supernova, we see at very large distances. And so if we get a sample of supernova calibrated through our bootstrapping with the Cepheid variables and the ray giant branch, then we can look at this Hubble parameter, the velocity divided by the distance for each of these supernova. We can get a plot like I'm showing over here with something called, in this case, the union to compilation of supernova. Each dot here is a supernova event, represents a supernova event where we have then a velocity at a distance. This is redshift down here. And through this mechanism, and with the assumption now of getting to cosmological distances, so I've got a model in here. But we've got these kind of values for the Hubble constant early on. And most recently, with Cosmic Force 3, I'm getting this value, we're getting this value down here. Now, I will go on to my next slide to just introduce what the controversy is all about. So there's 2 values of the Hubble constant that are being talked about right now. The people who were looking at the microwave background and the standard model of cosmology are promoting the idea that the Hubble constant is around 67, with quite small error bars. Now there's a group that's been making a great effort to determine the Hubble constant, led by Adam Rees, basically, who are coming up with this value of 73. Here's the short version of how they got that. They have, locally, they have calibrators within our own galaxy of Cepheids. They can then look at galaxies nearby to us, 18 galaxies nearby to us, that have had a supernova event, and they have measured Cepheid variables in those galaxies, and so they can extend their calibration through those to the supernova through those Cepheids, and then they can look at a sample of supernova, and they can extend out their calibration and get this value of 73. And the argument is now that this is looking like a situation where we have a conflict here that may indicate some new physics for beyond the standard model. I just wanted to emphasize that, so my value is a little bit larger, but if I plot this plot here, this is the distances. I'm using the astronomical term distance modulus here, the logarithmic distances for supernova here. And here, so I've attempted to scale and put the supernova on a proper scale here. And I'm looking here at the difference between the distance modulus from the supernova and the distance modulus I have from other techniques up here. And if I've got proper calibration, then things would lie at 0 here. Now what I'm plotting here, first of all, the blue points here are same Cepheid information as Reese has. So this is Reese's information. Over here, what I've got is a situation where I've got groups of galaxies. A supernova goes off in a group of galaxies where I have alternate distances. If it's in red, I have at least 3 alternate distances. And so what you see here then is that if I take the ensemble, I get this Hubble constant. If I only use the blue objects here, I get 73, just like Reese. So I don't have any disagreement I don't have any disagreement with this calibration. All I offer is if you look at this larger but less homogeneous data, I get a slightly different answer. Okay. Here's the final word I'm going to say on Hubble constant. So here's Cosmic Flows 3 map showing a map on the sky. If I look at the peculiar velocities from that sample, and I assume a Hubble constant of 75, then I get this histogram of peculiar velocities. And you can see that it's pretty well centered around 0. Now I can break that down according to distance, as I've got here. So what I'm plotting here then is peculiar velocity, the mean peculiar velocities in bins as I go out in distance. Here's the case so it would be then the case that anything that lies below this dotted line would suggest an infall, and anything above this dotted line would be suggestive of an outflow. As you see here with the choice 75, I've got a situation where nearby I have a little bit of infall, a little bit of outflow, far out, but not bad. The way a criterion you might like would be that this be flat with distance. That would be the 0th order expectation. And you would get that if you went to Hubble constant of 76 or so. Then you would see something that was rather flat going across here with distance. Except that you would also see that would be implying infall at all distances. You might not like that. And if you took 73, here's 73, you're starting to see an outflow at large distances. If you go to 68, or imagine that I plotted up here 67, you can see that I've got something ridiculous. I've got a huge outflow, which is, and you can see that the implication is simply that you're taking the wrong Hubble constant. I'd be seeing an outflow here of 700 kilometers per second if I took a Hubble constant of 68. So the takeaway from this is the only way I can imagine saving 68, 67 as I evaluate the Hubble constant is to say that we're totally messing up on the 0 point of all of this calibration at the level of 10%. I don't really think that's happening, but then I offer that evidence. So basically then we appear to have something going on. Either we're messing up entirely with our measurements of distances, or they're making a mistake here, or there's new physics which is of course the interesting possibility. Okay, let me wind up here then with this discussion of Laniakea, was the title. First of all, I'm showing here something that Yehuda Hoffman led us on. There's a flow across the whole region that we've been talking about, flowing across to an entity that's been called the Shapley concentration. And here's the bulk flow measurements that we've been making here. Most of the data is in here. The dashed lines are the expectation of the standard lambda CDM model. The solid line is what we're observing. It's a little bit high in here, but it's not so high as to be really a crisis for lambda CDM. So I've then been looking at these peculiar velocities and defining structure, which I'm showing here some pictures, pretty pictures, and we ended up discussing defining Laniakea. Now, Laniakea, here we are, here is us sitting here on planet Earth in our galaxy. The zone of obscuration of our galaxy runs across here. What we've reconstructed here is the density that comes from the peculiar velocity field, so that we have detailed reconstructions nearby, which is why we get this high point here. But over here, there's a general region that's higher density. Then there are voids, and then there are these higher densities here. And these little lines here are showing flow lines. And what we found then, so it had been known for quite a while that we've been moving in this direction over here towards Shapley, ever since really the information came from the microwave background dipole that we're moving in this direction over here. But now what we're seeing locally then is the way that these flows are splitting up, such that if you're inside this boundary, the local flows are inward. And if you're outside that boundary, local flows are outward. And so we define the region of our inward motions in 3 dimensions, the Laniakea supercluster. Has 10 to the 17 solar masses, it extends across 160 megaparsecs. It's pretty big. So here's some other pictures of it, variations of it. And what I've got here, let's see. I have some movies now. And how am I doing on time? So what do we got, about 20 minutes? Is that, or a little bit less? 10, yeah. This movie is a little bit long, but let's start into it. This was done so just to orient ourselves here, here's all the galaxies from redshift survey nearby, and here's the zone of obscuration where we're not seeing any galaxies. And at some point here, it'll do a little rotation and we'll go in to see our own place here. I think, so here's the galaxies in cosmic flows too that we had distances for. Anything in red there has a peculiar velocity away from us. Anything in blue has a peculiar velocity toward us. So all of this reconstruction I'm talking about comes from that data. And then we do these reconstructions. So as it says down here we are up here, this is us down here, and there are these flows going across to this region over here, which has become called the Shapley concentration. This is over here, a region called Perseus Pisces. But I think, so here's some of these reconstructions of the density field. But I'm going to go on here. And I'm going to go on here. Here's another little music on this one. But I'm going to pass on this one too. But I'm going to stick with this one. Let me see, how do you make that quiet? A little bit quieter. What do I have to do? I have to maybe I have to do something like this. Oh, maybe I can. Yes, I'd rather So,
what you are seeing are surfaces of filaments and knots, elements of the cosmic view web along with sheets and voids. This construction is based on observations of the velocities of galaxies as they deviate from the universal expansion. 8,000 distances and inferred deviant velocities are modeled as a field of three-dimensional velocities and densities. Reconstruction and constrained realizations satisfy the data and the standard model of cosmology. The cosmic view web is derived by calculating the shear and the velocity field on a three-dimensional
the point
grid.
here is that this is all from velocity.
Shear indicating equal on three orthogonal axes identifies the grid position as part of the knot. Outflow on all three axes is the signature of a void position. In between are filaments, collapse on two axes, and sheets, collapse on one axis. Surfaces can be defined that enclose knots and filaments and, if desired, sheets and voids. The scale of the reconstruction exceeds 1 billion light-years. Names are given to major components.
Shot plate. We're buried in here, middle.
Global deviant velocity flow lines revealed by the Wiener filter analysis are shown from selected seed positions. A flow line is constructed by stepping from an initial seed location in the direction of the deviant motion at that point, then taking further steps following the path of motions at each new points. The flow lines are given colors according to local velocity. Velocities increase, redder rainbow colors, as a knot is approached, and decrease, bluer colors, in passing through the potential minimum of the basin of attraction. It is seen that all the global flow lines terminate at the feature called shapely. The flows now being shown are local. Global flows can be broken down into local flows due to mass within a restricted region and tidal flows due to everything outside the specified region. A region from Perseus-Pisces through the funnel is highlighted. Local flows proceed along filaments to nearby knots. Flows along filaments need not be one way. There can be a divergent point along a filament with local flows heading in opposite directions towards separate knots. Global flows specific to the Perseus-Pisces to Lepus region are shown again. Global flows from Perseus-Pisces and the Southern will gather at the funnel and proceed through Lepus to Shapely. We return to the visualization of local flows. Individual galaxies from a redshift survey are superimposed. Now only galaxies associated with groups of at least 10 members are shown to simplify the presentation. Local flows are shown. The zoom inward gives focus to the heart of the Perseus-Pisces region, where there is a string of significant clusters culminating in the Perseus cluster. The Perseus coma filament is highlighted. This structure is poorly seen in the distribution of galaxies because it lies behind the plane of the Milky Way, but it is well defined by the Wiener filtering of galaxy motions. There is a divergence of flows along the filament, breaking toward either Perseus-Pisces or coma. Hercules shapely filament is highlighted. Local flows shear toward Hercules or shapely, but the global flow pattern seeded in Hercules proceeds in one direction to shapely. The highlight is now on the great attractor and the major pervadus filament feeding into it from Indus. The arch is highlighted. This filament at the roof of the local void links between two great structures with a divergence between local flows toward Perseus Pisces and through Indus to the great attractor. The zoom inward gives attention to the Angius strand, another filament running between the great attractor and Perseus Pisces. This filament is difficult to follow in the distribution of galaxies because it passes behind the zone of obscuration, but it is well defined in the V-web. In the background is the Virgo strand, the direct link between our galaxy and the great attractor. Our galaxy, the Milky Way, lies at the origin of the red, green, blue arrows. A rotation and further zoom gives a clearer view of our linkage to the great attractor in the region of the Centaurus and Norma clusters. The clusters appear slightly displaced from the V-web because of offsets between measured distances and distances inferred from redsheds. Laniakea, the full basin of attraction of the great attractor, is shown as a silhouette within the V-web. We have been looking at the exterior surfaces of the V-web filaments. Let us go inside. Perseus Pisces, a node of the cosmic V-web where several filaments converge. The insert helps with orientation. The flashing yellow ball identifies the current viewing location. Only galaxies in important groups are shown as individual little spheres. We enter the filament connecting Perseus Pisces to Coma in the Great Wall. Coma, a node of the V-web filament system. The great attractor at the heart of Laniakea. Inside the Virgo filament, the Virgo cluster and the local group. White spheres provide a more complete rendition of galaxies near home.
So these surfaces, as you can appreciate, are
from the heart of Laniakea into the Babylon's filament.
that define filaments.
The Perseus-Pisces filament. Large copper balls represent entire rich clusters of galaxies. Onward to Lepus. Onward to the Shapley concentration. Shapley, the densest nearby concentration of galaxy clusters. Shapley is the dominant sink of velocity flows.
This is 4 minutes
Somewhere in
long.
the universe
Okay.
is a small blue planet. The third rock from the star called the Sun. Just one of billions of stars in a spiral galaxy known as the Milky Way. But where in the universe is the Milky Way? A team of scientists gathered data on more than 8,000 of the galaxies that surround us. They mapped each galaxy's position and movement in space. And, for the first time, they've shown that the Milky Way is part of a much larger system of galaxies, a supercluster that they have named Laniakea. The Milky Way is nested in the furthest reaches of this structure, on the outskirts. The entire universe can be seen as an intricate network of galaxies, a cosmic web. Some areas are almost empty, dark voids. Others are densely packed with galaxies in regions known as superclusters. Superclusters are the biggest structures found in the universe, but scientists have struggled to define where one ends and another begins. To map our home supercluster, a team led by Brent Tully at the University of Hawaii studied the motions of the galaxies around us in unprecedented detail. Even though the entire universe is expanding rapidly, gravity is also at work, pulling against this acceleration. By discounting cosmic expansion, the team worked out which galaxies are being pulled towards us, shown in blue, and which are being pulled away, shown in red. This enabled them to create a map of cosmic flows, the paths that galaxies migrate along, tugged at a tiny pace by the force of gravity. Using this motion, they came up with a new way to map the distribution of matter in the universe. Delving into our home supercluster, you can see that most galaxies are being pulled towards a dense centre. This is known as the Great Attractor. Our galaxy is among those sliding towards this patch of space, which dominates our region of the universe. Let's take a different view. Each circle represents a galaxy. Again, we can see most galaxies being pulled towards the Great Attractor, in the direction of the arrows. Between the Great Attractor and us, the Milky Way, is a relatively empty area, a blue void. And next to us is Virgo, a large and dense cluster whose bright galaxies have been observed from Earth for centuries. Until now, astronomers grouped us, the Milky Way and its surrounding galaxies, with Virgo and nearly 100 other clusters in a supercluster that stretches 100 million light years across. But using this new technique, we can see that this is just the tip of the iceberg. This cluster of clusters is merely an appendage of a much larger supercluster, more than 100 times bigger and more massive. How did the team know how to redraw the boundaries of this cosmic map? Here's our supercluster in black and a neighbouring structure, Perseus Pisces, in red. Scientists define the boundary as the points where the flows of galaxies diverge, like water dividing at a watershed. This is where neighbouring structures shear apart. This is the first clear definition of a supercluster. Laniakea means immeasurable heaven in Hawaiian, a fitting name for the vast community of galaxies that we are a part of. So now we know that on the edge of a supercluster called Laniakea, in a galaxy called the Milky Way, around a star we call the Sun, there is a small blue planet, our home.
Okay, that's the story of Laniakea.